Hello everyone, welcome to Computer Science in Yoruba and English. Today we're going to be looking at a very important finite state machine called push down automata. So basically I'm assuming that you already have some basic knowledge about the deterministic finite automata and maybe the non-deterministic finite automata. So this is a very important and a very more efficient finite state machine that has extra memory. So just when you think about PDA, push down automata, we should think about it as a finite state machine that has an extra memory. So that is actually what gives it a leverage over that. So let's just go straight into business. So basically push down automata, a lot of people often get confused, but it happens to be a very interesting concept once you understand the rudiments. So basically there are some things that you need to, I want to try and make this video as short as possible, so I'm going to just start the most important things. And basically I'd like to mention that before you can actually talk about push down automata, there are some things that you need to understand if you're going to be working with the concept itself. So basically, like I said, a push down automata is a finite state machine and has an extra memory. In some cases you can call it infinite memory because of the way you use it in computations and stuff like that. So some of the limitations of deterministic finite automata is what actually led into using or the concept of push down automata. So, and it has actually proved very efficient, although not as much as efficient as a Turing machine, but is actually much more efficient than the deterministic finite automata. So basically here we want to look into the concept, or let me say the prerequisites, things that you should know if you were to work on this. So basically the formal definition of a PDA is said to be a 7-tuple, and you can say multiples of 7. Yeah, so basically the definition goes thus, where you have okay, let me use the writing tool. Okay, so the definition goes thus, where you have let's say PDA. So you have a definition such that you have Q, you have your sigma, you have your S, you have your delta, which is a transition function, you have your Q naught, which is your start state, you have your I, which is your topmost element in your stack, and you have your F, which is your final state. So all those things are things that I would eventually explain what they mean to you. So basically let me go back to this. So when we say Q, just like I said, Q is let's say a finite set of states. So you can have state Q1, Q2, state A, state B. So let's just say a finite set of states, or your set of states. But one thing that's very important is for you to know that it's actually excuse me, is actually finite. So you can't have them infinitely. It's actually just the same as the normal state machines that you know. So it's just that one of the advantages it has is the fact that you have a stack that you can work with. You can store items, you can retrieve items, and do some manipulations to know whether a language actually fits in to the category of language defined or it is rejected. So we have sigma, and that is defined as we can say a finite set of symbols. So let's say a finite set of symbols, and when I say symbols here, some people call it elements, and basically symbols mean when it can actually be confusing because we still have the S, and the S is actually symbols too, but the symbols here, the difference between symbol here and the symbol here is the fact that the symbol here are symbols of the language itself. So let's say, let me just say symbols permitted by the language. So let's say English language, for instance. Now ABC are the permitted languages, and so if you are given a word, I can't have an English word and I want to say let me spell a car, and now say C B, or let's say C1R, because 1 doesn't fit into the set of symbols permitted in English. So it means that it doesn't fit into that category. So the symbols we're talking here depends on whatever language you're trying to work with. So but the symbols we are dealing with here, in some cases, is actually very, very confusing. That's why I'm trying to clarify this. So the symbol we have here talks about the symbol we are using in our stack for our operations. So in some cases they're actually the same, because you take those same symbols, you want to work with them, but it depends on your approach of solving or defining an automaton. You might actually want to differentiate. For instance, if you are working with set of symbols A, B, C, during your stack operations you can decide to use 1, 2, 3 and stuff like that. You can decide to use 0, 1. You can decide to use anything that pleases you just to solve the problem. But in most cases, and in this very scenario, and for the sake of this demonstration, I will be using the same symbols that I receive that's permitted in my language. I will be using it for my stack operations too. So let's say S is a set of symbols in the stack, and I have my delta, which is my transition function, such that you have your set state, and you have it mapped to either sigma itself. I don't know how to represent that, so let me just put that in writing so that you can use the board. So I have that such that I have this, and is mapped to either one of the symbols or an empty set. So that's one of the major difference between this and a DFA, because that you cannot have an epsilon in that. A DFA does not accept an epsilon as part of the elements in the transition, but here you can accept that, and you have a symbol from the stack, then you produce a final state eventually. So we're going to see how this works eventually. So that's the transition, and we have the Q naught. I wouldn't know how to represent that here, but let me just say, yeah, let me just define it. So I have Q naught as my start state, just like so the start state, and I have I, and this is very important. You have to I means we use I for representing the topmost element in the stack, and we use F as, just as the final state. And this could be multiple. We can have more than one final state. So this is the formal definition of a. So saying, we can say F belongs to is a subset of F is a subset of Q. I is a subset of S. Yes, of S. I beg your pardon. Yes. So, and Q is also a subset of Q. I mean Q naught, I beg your pardon, Q naught. Let me use a small letter Q here so that you see. So Q naught is a subset of Q. So that's how it works. So basically, let me just don't worry, don't panic if you don't understand what I'm saying right now, because we're going to take example, and at the end of these, hopefully you will have a clear understanding of how it works, and you'll be able to take up an example yourself and address the problem. So having said that, there's another important thing that we need to know. Here, and which are the stack operations. So I like to talk about this, and because this understanding of these things, a very good understanding of these things, actually gives you a leverage when dealing with these things. If you try to miss any of these concepts, you might be having issues eventually in doing in building or constructing a push down automator. So the stack operations, so basically we have primarily we define the push and the pop, but in some cases, because in the scenario where we're actually working, a realistic scenario, let's say we actually do much more than that, because it's not understanding push and pop alone, although the two other ones that I'm about to add so that you can have an understanding is still based on push and pop, but you need to know them so that you know which one is much more appropriate in the scenario you find yourself. So let's say you have a push, and we can say this is just a process of pushing or adding, the process of adding an element to the stack. So it can be an element, a symbol, just as we've been using here, symbol. So we have pop. So it's just simple as you're popping or you're removing an item from the stack. And here I want to tell you that there's another thing that we do here. It's called swap or replacement. It's still based on these two, and this is a combination of popping and pushing. So we can say pop and push. So basically, let me just say this one means that you're removing one item and adding another item. So, and we have no operation at all. So this no operation, so basically how we use this I'm going to show you in a bit. So, but just know that there is these 4 things that you need to understand for you to be able to deal with issues or scenarios or whichever question you're given in this. So a very good understanding of these 4 operations will really help you and will enable you address whichever issue, knowing the right operation at the right time. So having said that, let me go just get rid of this. Okay, yeah, so like I said, so let's just try and conceptualize the push down automator. Let's say you have a bucket or a stack. Precisely, this stack is actually meant to help you, just like the name. I'm very sure if you have a very good understanding of how data structure works, I'm very sure this is not going to be new to you, so you understand how stack works already. So in a stack, the structure of a stack in data structure in computer science is that you can only remove an item from the top. So if you're going to be removing an item, you can only remove an item from the top here. The topmost element is where you can remove an item, and if you're adding an item also, you can only add it from the top to the top. So if you have any reason to remove the item that is at the bottommost part of the stack, it means that you have no choice. You have to find a way to remove this, to remove this, to remove this, to remove this, all the items before you can get here and say you want to remove this. There is no magic. That's how a stack works. So having understood how stack works, and let's just say we have an input step, and basically its job is just to read your items. So if you have a language that defines a word, blah blah, and you can actually insert the word. Let's say a word is W equals BA. So this, you are lifting it from here and you are putting it inside the input step. So the input step still has something to work with here, which is a finite automata itself, or let's say the finite automata. So it actually works with this, and it is this one that will decide on what to do based on the transition function that you have defined. So this one, it gives one of these to this. This machine determines what to do based on a particular defined criteria. So this one will determine whether to come here to remove an item or to add a new item, whichever the case is. So basically that's how the stuff works. So let me just use so that you can have a clear understanding. I know that's what some of you are waiting for. You want practical examples. So let's say, for instance, if you have let me use this very common, very popular example. And if you have a language such that, let's say, a raised to the power of n, b raised to the power of n. Okay, let me erase all this so that we can have much space to work. So we have a raised to the power of n. We have a raised to the power of n, b raised to the power of n, such that n is greater than 0. This is one scenario, and it could be actually n greater than or equal to 0. It could be anything based on, so it's just a language. So this is the rule. So you are actually meant, your assignment or your task is to, to build this automata in such a way that it accepts or identifies if a certain word has passed this criteria. So how do we do that? If you look at it closely, you see that we have n. N is just an arbitrary number, and we don't know how large it is. And but because we don't know how large it is, we don't know how small it is. But come to think of it, if we have a deterministic finite automata, if we are saying that accept 2a, then 3b, we know that we can actually maneuver and build the automaton such that we have a machine that accepts or rejects that language. But in this case, you never know. We don't even know what n is, like I said. So we need to use our understanding of the push down automaton to solve this problem. So let me erase this. So let's just quickly go into addressing this problem. And let's say, first, what I'd recommend you do is, no matter what, if you are given a language, if you don't even understand the sets or let me say words that belong to that language that passes that test, it is practically impossible to solve that problem. So if you are given a raised to power n, you must define some some sample values that fit into the category of, so that gives you a clear understanding of what the language or what the words in that language should look like. So let's say we said a raised to the power of n, b raised to the power of n, such that n greater than or equals to 0. That's our L, and we're saying a b b. It passes this test. A B B B. Oh, sorry, beg your pardon. B B B. It passes this test. And what am I trying to do? The rule says that the same n and n is the same. I did not say n or b. N and n is the same arbitrary number. So if you have 3 A's, you have to have 3 B's. If you have 0 A's, you have to have 0 B. If you have 10 A's, you have to have 10 B's following each other. So if you have B, or let's say, I beg your pardon. So if you have A B B B B, whatever you're defining, you have to make sure that they are equal. The numbers of A is equal to the numbers of B, so that way the language is accepted no matter what. And as a matter of fact, we have epsilon also is also a member of this language. So but if you have something like A, B, 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 this one will definitely fail this test. So how do we go about constructing this? So basically, if you look at this is actually one of the simplest tasks you can get in a PDA. And if you look at this, basically all we need to do, okay, maybe before I go on, I need to talk about the acceptability criteria of a PDA. So a PDA is accepted if you're able to read all the inputs and get to a final state. I don't know if you, so it is accepted if you're able to read all the inputs and get to a final state, and also if you're able to exhaust all the inputs but you are not stuck. You can also accept the word, the given word. But in most cases you are able to read the final state if you actually build your, not all automata actually passes that criteria. So let's say you have a state q naught. So basically what we are trying to do here, if you look at it conceptually, even before we approach this problem, it simply means if I'm able to add 3 A's, then somehow if I design my automaton in such a way that it can accept, you can add 3 A's to the stack, and the next thing my automaton is expecting is 3 B's. So all I need to do is make sure that it adds 3B, exactly 3B. So at the point of adding the 4th B, already I'm either stuck or not even reaching the endpoint. So at the same time, I need to talk about the reject criteria of a PDA. So it means that a PDA, you reject a PDA if you are stuck. If you get to a particular state such as Q naught and there is no move to make, no move to make, so it is sufficient to say that the language is rejected. So that alone is sufficient to say that a language is rejected when you are stuck and no move to make, or you read all the inputs and you were unable to reach. If you're unable to read the final, if you read all the inputs, you're likely to still accept the language. So what do we do now? Let's go ahead to build this automaton. Okay, let me get rid of this. Okay, so let's say we have Q naught, and what do we want to do? Let me quickly tell you that there's this trick. We want to say it's some of the many approaches, or let me say one of the many approaches that we have in building a push down automaton. And you have it such that it is assumed that before you start any operation, you don't want the stack to be empty, so you add an arbitrary $sign to your stack. It could be anything. You can add an alpha, you can add a beta, you can add anything, so that you can check. The moment you see this kind of element, whatever you've chosen to add, the moment you see it in your stack, you're able to read such that you're actually picking, picking, I'm very sure maybe you understand this. Picking means that you actually, is like you are spying on what you have on top of the stack. So if you're able to pick the stack and you see any of this as you may have used it, it means that the stack is empty. So then you can use that to decide whatever you want to do at that point. So like I said, we'll take examples. Let me get rid of this. Okay, so we have Q naught, and I have this as my start state. Let me quickly conceptualize it so that I have my stack on my right hand side here. And basically what I want to do here is I want to keep, the first thing I want to do at state Q naught is that I want to add an how do I put this? I want to add the symbol we just discussed, which is, it could be dollar, it could be anything you're choosing to use. You want to add it to your stack the first time, nothing more, nothing less. So we are saying epsilon, and the top of the stack is epsilon. You want to say we want to add this guy. So let me quickly talk about the representation of these three characters we have here. So in the operations of a push down automaton, we have it such that you have these three pairs, and we say that the first one is your input belonging to sigma. The second one is your topmost elements on your stack, and the third one is what you are pushing. So basically, if you are saying epsilon, what I'm doing here, I'm simply pushing. So because I'm pushing the dollar sign regardless, I'm saying that if I'm receiving inputs of epsilon and have my topmost element of my stack epsilon, which simply I'm saying if it is empty, and by default my stack is empty, so it means that I want to add this guy. So this transition brings this thing all the way to this stack the first time. That is what it does. So let me take it back. Okay, so at this point I want to move to the next state, Q1, and what I'm actually doing at this point is very, very simple. I want to say that if I have Q in my Q1, because the language already states a raised to the power of n, b raised to the power of n, such that n greater than or equals to 0. So I know for sure that the element that is coming into the stack is a. If it is not an a, it is sufficient to say that that language fails the test. But there's actually one thing that we need to take care of. I'll talk about it before we finish this very session. So we can say a, if a comes here, I want to keep looping. I want to keep reading as long as a is in this content. So if I have a, for instance, b, I want to add a. If the second item is a, I want to remain in this state Q1. If the third one is a, I want to remain in this state Q1. The only thing that will make this thing leave this state Q1 is if I receive any other thing other than a. That is, and if I receive anything that other than a, it should be b definitely. If it is not a b, it means that it is sufficient to say that that whatever word w is, it is sufficient to say that it has failed this test, and so we can say the word has been rejected. So we can actually say a, if what we receive is a and the topmost element of the stack empty, which is always correct about that, and we want to, no, sorry, I beg your pardon, I don't want to push the dollar sign, I want to push a. So, and before I proceed, there's something that I must have skipped. I need to quickly talk about how you do this operation. I talked about pop, push, swap, and nothing the other times. I was supposed to tell you how this representation works in transitioning. So basically, if you have a pop operation always follows the first element, could be anything you are receiving in a pop operation. Let me quickly define this. So in a pop operation, the format is usually any input epsilon, then the new input, or let's say let's say the item, new item. Let's say new item. So what am I trying to say? Any input could be A, but it must be followed by an epsilon, and my new item could be B. It could be anything. It could be A itself. It could be anything. It could be the same with this. It doesn't really matter. But it is very important that you have epsilon in the middle. That means that you are doing a pop operation. So I beg your pardon, I was supposed to say a push operation. You are pushing. You are pushing. You are pushing here. So that is push. So everything we have here is push operation. So if you have pop operation, so with pop actually is when you have any input and you have a valid item. Yeah, it could be A, or let's say let me use the word valid. I'll explain what I mean by valid. Okay. Okay, B, and you have epsilon. You have epsilon. If you have anything in this format, it means that you must have an item here followed by an epsilon. It means that you are doing a pop operation. So if you are doing a swap operation, if you are doing a swap operation, the only difference between pop and swap is that the second and the last symbol here they will not be epsilon. So which means just as you have a valid item here, a valid symbol here, you also have a valid symbol here. So it could be any inputs, then B, then C. So this is a swap. So it means that you are swapping B with C. If you look at the second one, the pop operation, it's also a swap operation, but basically what you are doing is that you are swapping B with epsilon. And if you look at it in the real sense, what you are doing is you are removing B. If you are swapping B with epsilon, what are you doing? You are removing you are swapping B with an empty word. So basically you are removing the B, so it's basically popping it out. So and the no operation means that when you have epsilon, just a moment, let me write properly. So when you have epsilon, or no sorry, you have it could be anything actually. So when you have an input, which could be anything, followed by epsilon, and definitely followed by an epsilon, it means that nothing, this kind of function will have no effect. So that is why I called it no operation. So these are the things that we're going to leverage on to be able to solve our PDA quest. So let's go back to our automaton. So now that we understand how that works, so basically, like I said, if you remember, A, epsilon, it means that I received A, and regardless, I intentionally put epsilon in the middle. So which means regardless, I'm not ready to swap. I want to keep pushing. I want to keep pushing as long as I have A as my input. So that's why epsilon is there. So the only reason why this condition will not run, this loop will not run, is when I have anything other than A. And when I don't have an A, I'm expected to have a B. So if I don't have a B, I'm stuck at Q1 because there will be no move to make. So the only provision I'm making here is B. So if I receive a B and the topmost element is A, which should be the right thing to happen. So what I want to do is I want to remove A. And if you see from the definition of what I just described now, we are doing a pop operation now. Initially we were doing push, and now we are doing pop. So because we have an element here and we have epsilon at the end, so we are doing pop, and I want to pop until the stack is empty. So what do? I have another state. The moment I pop, I want to move to state Q2, and from state Q2 I want to say, okay, let me keep popping, but this pop is not sufficient. The one I wrote here is not sufficient to do this, so I have to run a loop right inside here to go back here to repeat this same pop operation. B, A, then pop it, replace it with epsilon, so I have it moving to the next state, which is likely to be my final state. So once I pop here, I receive B. The only thing that will make this thing stop receiving or stop running is when I don't receive a B. But not that alone. When I don't receive a B, it will check if the topmost element is A. But no, this condition will never be true. So it will come here. Definitely, the moment I stop receiving a B, it means that the language, all the characters have been read, and basically the next thing that my automaton will read is epsilon, which is empty, which means all the words have been read. So I want to see at the point I'm reading an empty word or an empty character, epsilon, and I see this character $, the same that we pushed here. It means that I want to pop $, out of my stack. So I'm able to accept this Q3, and with this I'm done. So let's quickly practicalize this. I have A, B, B, B. Let me erase this so that we can see. Okay, so my stack at the initial stage in Q0, I have I'm adding $, which is what I have at the topmost part here, and from there I'm moving to Q1. So Q1, I'm reading A. I get to this function here where I want to read A. I read A. I read this A. I want to keep pushing A to the stack because I have epsilon in the middle. So it means that regardless, I don't care what is on top of the stack. Technically speaking, I'm saying that just add, because my stack is not actually empty. If I want to say it has a $sign. So but like that's why I said if you have an epsilon in the middle of those pairs, of that pair, it means that you are pushing regardless. So I push A to this. Let me mark this. Once I push A, I'm still reading A again. The next thing on the tape, let me just segment this, or let me write it in form of a tape so that we understand better. A, B, B, B. So I've read this, and the next thing I want to read is A. So if you look at it closely, you see that I will remain in this part still. So I read this, I remain in what state? State Q1, and I read it again, I remain in state Q1 regardless. But I receive B now. Look at it. Once I receive B, this is where I'll find myself because A is no longer read. So once I find myself here, what is the condition? I've read A here already, I've read A here already. So the condition says that if I have B as input, which is correct here, and the topmost stack is A, which is correct here, I want to do what? I want to pop A out, which means I want to make A an epsilon. So what do I want to do here? let me not delete it so that we can see clearly. Let me cross it out. So let me use this. Let me cross it out. And what am I saying? I'm reading B again. What do? I still want to cross it out. I'm reading B again. I want to cross it out. And now if you look at it, there's an epsilon here because the input tape is now empty. I read an epsilon. I've crossed this out. I read an epsilon, and the bottommost element is $. Then what do I want to do? I want to also cross $. out. And this, because this language, or this particular word, this particular W equals AAABBB, actually takes me to the final state. And so that is what our automaton looks like. So to make it cleaner, I'm going to quickly draw the automaton again so that we can see what it looks like. So I say we have start, we have Q0, we go here, we have Q1, we go here, we have Q2, and we come here, we have Q3, which is our final state. So we want to add epsilon regardless. We want to add $sign regardless. Here we want to check if A is red. I want to keep popping, or I want to keep pushing an A. So the same condition I'm going to repeat here. If A, I want to keep, I beg your pardon. If B and I have epsilon, I want to remove, and I have a A, I want to pop it. I want to repeat this condition here. So I'm going to say B, A, then pop it. And lastly, I want to say if it's epsilon, and if it's epsilon and I have my $sign, then I want to pop the epsilon, and that brings me to the state. So languages like A, B, 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 or the words like A, B, 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 let's say A, B, 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 A will be accepted. This will be rejected. A, B, B, B. This will be rejected. But if you look at this actually solves our problem. But there's one thing still missing, because the language says A raised to the power of n, B raised to the power of n, such that n greater than or equals to 0. The condition greater than or equals to means that even the empty word satisfies this condition. So I'm going to make this and accept states also. So, and with that, we have a completed automaton. So in the meantime, if you have questions, recommendations, additions, subtractions, reservations as regards any of the concepts we touched in this lecture, kindly use the comment section below, or you can send us a mail at csctutes@gmail.com.